Um, I hope everybody can see the screen. Thank you all for coming and attending. I've given 7 webinars for the Copper and Brass Service Center Association previously, and several of them have covered similar territory as far as casting techniques and so forth. However, this one goes a little further in several different directions, and I think it'll be good as an extension of what we've talked about previously in some of those other earlier webinars. Well, I often start with a slide, this slide. I like this illustration. It's off of a piece of pottery from Egypt. There are similar illustrations to this off of pottery from Greece and various other areas in the Middle East way back, of how metals were melted, put in a crucible, and then poured into molds in ancient times. Obviously, we wear better protective gear, and we do it a little different these days. Historically, metals processing in ancient times, they were processed consisted of beating native materials with rocks. That sounds primitive, but since they really had no melting facilities, even as we've just seen, that had to be developed. Native copper was found essentially as a green or bluish rock just laying on the ground. If they took said rock and pounded it with a rock tool or hammer, they would be able to form it into various things. Generally and initially, they formed bowls and other utensils for use. They also formed decorative objects, became jewelry, and highly prized. Later on, a couple millennia later, the discovery of bronze, copper plus tin, increased the utility of the materials. Tools could be formed using bronze because it would retain a good edge. You could use it as a knife. Usually they had to use flint tools or tools made out of volcanic glass, obsidian. In historic metal processing, much of it was casting when they melted it, casting to shape. Later, it was casting with some type of working. They cast it into a shape. Often, again, they would work it with those primitive tools into the final shape that they would like. And ancient processing was somewhat region-specific. Europe and India seem to have developed casting and wrought processing. In other words, they would be able to hammer it or roll it or do something with it afterwards, or they had learned how to do that. Other regions, such as China and the Americas, both North and South, there was only evidence that casting was done early on. That was supplanted when people started moving between continents. Well, when we come to today's metal processing, we do casting to shape, although we do a much better job and we have better molds these days. We do something called continuous casting, and the development of that has been very beneficial. Casting with subsequent processing, and by this sometimes you take a continuous cast piece or a cast to shape piece and you do some minor machining, finishing, drilling, things like that to make it workable. Well, another way to do it is casting a basic shape followed by wrought processing. We've discussed that previously, where you, in the making of sheet mill products, you cast in the copper industry what you call a cake or a slab, usually 4 to 7 inches thick, and then you roll that down. Likewise, you can use cast shapes, rolling or processing down in other areas. Again, you cast something and then forge it. In other words, forging is a very large hammer, usually on a heated piece of metal, or you can use powdered metals, which is a development in the 20th century and on. So there's many ways you can do things. In a mill or in the plant, we transform various materials, scrap, pure metals, and additives, small additions, into semi-finished products for use. Several steps in the processing of this material are taken. And the final product, the alloy, there's over 850 copper alloys, so there's lots of those. The size, the shape are pretty much dictated by an agreement between the customer and the producer. Usually written down and specified by an ASTM specification. Well, processing in different mills takes place in different ways, obviously. Not everyone makes all shapes, sizes of materials. Many final products can be made, like flat products. Sheet, strip, plate. Usually start, as I said earlier, with a cake. You roll that down, and if you don't go too far, you can make a plate. If you roll it down further, you make sheet, or can make sheet. And if you slit that into narrower widths, you make strip. Round products. Rod can be made either from a strip and rolled and welded into shape, or cast as a tube. Rod can be cast directly, and it used to be rolled out of a bar. And wire, again, wire was rolled out of rod, which was made out of a cast shape. These days, we'll look at a couple production techniques for round products. Shapes, rod, tube, hex, and other shapes. You can make rod or tube with flutes, with multiple sides, not only hexagonal, but variety of other shapes. They can be fluted and cut off and used as gears. So there's many things that can be done. Cast shapes. These are static molds or reusable molds. Cast the shape and then finished, as I said earlier, or you can use these as a prep for forgings, which you cast an initial shape and then you take it to the forge, probably preheat, and then hit it a variety of times to make the final product. And then powder compacted shapes. Powder metallurgy can be made into, or using a variety of metal powders, and you can get many different alloys that way as well. Some that you can't make in a regular furnace. We'll talk here about continuous casting, and I've done that previously. There's a variety of casting techniques that are considered continuous. There's wheel casting, which is primarily used for rod and round shapes. Upcasting, which is again a rod, but can be used for, you can upcast a rod fairly large and then flatten it into a strip. So it's not absolutely just a round product. Vertical casting, usually in a continuous form, this is a vertical drop, as opposed to the upcasting techniques. And then horizontal continuous casting. Those are a specialty area many times for long solidification temperature alloys. I'd like to go through, and I've shown this before, a typical series showing how a continuous rod process works. At one end, you load raw material. In this case, it's shown as cathode, but it can be used or can be mixed material, loaded in this case, a shaft furnace, but you can use other types of furnaces. You can run it through various launders, holding furnaces, and lower launders. And in this case, you can run it from a pouring pot into a casting wheel. This is generally a Properzy process or a wheel process. Get a copper bar out, and depending upon the shape of the wheel, you can get different configurations coming out. Then you let it solidify through the extractor and pinch rolls and rotary shears. You could cut it off, or you can do some finishing on it, cleaning, pickling, various wipes. You can cut it, wax it, coil it, and ship it. Or you can cut it into length and make other products out of it. Now, in the continuous cast rod production, another technique is upcasting. And this is a dip process. You basically have a rod or starter rod, usually steel and cooled, and you put this into a molten pool of copper, usually an electric furnace, and slowly extract it. The copper will freeze or solidify onto the beginning rod. It will travel upward, and you do this rather slowly. Now, like I said, the upcasting process, you can produce a rod, or, as this shows, you can roll it and make a strip. Depending upon how big or how big a diameter the rod is that you extract from this casting technique, you can flatten it and make 4 or 5 inch wide material, sometimes even a little wider. You do have to do some treatment and rolling, obviously, to get it down to the proper thickness. You may want to make a bar out of it. You may want to make some other material out of it. You may not want to cut it and just do some edge trimming. That's up to the thought process of the production facility. There is a vertical casting technique, and this is used in a number of applications. Now, in this particular instance, it's shown with a melting unit up top pouring into a holding furnace, and the molten metal is held. You do have to be careful, but you're pouring or extracting the molten metal out of the bottom of this furnace to get your actual material. So many of the impurities and other things float to the top of this holding furnace, and therefore you can have someone skimming that off. It doesn't get into the actual workpiece, the continuous cast bar or rod, as it's withdrawn from the bottom. This is a little misleading in that it gives you the impression that all you're going to be able to cast is a round product, and that it's very simplistic. And well, that's what the illustration is supposed to be, simplistic, so you can actually see what is going on. In reality, when something like this is in a plant, it's somewhat difficult to see and what exactly is happening, and you will see the beginning. Maybe you'll see a glow in the middle, and then you'll see after it's solidified and below what final shape you're coming to, and maybe you're extracting it and using an automatic saw to cut it to length and remove the workpiece, which is then allowed to fully solidify or cool before it's finalized as far as processing. There could be some subsequent processing in that you may have to clean it, and you may have to also finish the ends, or you may want to drill things or do other applications and or different finishing processes to it. Another high volume vertical casting technique, various shapes, as I pointed out, is this type of scheme. Again, you have a holding furnace or ladle, and the melting furnace in this particular instance is another furnace. And you have a tundish, and this is used in a variety of industries: steel, copper, and some others. And you're casting vertically down. The mold is at the top and it's water cooled. You have extraction rolls or drive rolls. And in this particular scheme, you are casting at a fairly high rate, or can. And if, as in the previous illustration, you can come down vertically for relatively short pieces if you have a lot of headspace in your facility, or you can bend it, such as you're seeing here when the material is still hot, to a horizontal plane. And all the while during this processing, where the curvature and putting it in a horizontal plane, you could be moving it into a slightly different shape. That's what all those rolls and curved racks are for. Then you have a straightener. In other words, you want it to come out straight. You don't want it to be curved or have camber or anything. This type of vertical caster, you could drop a wide variety of things. You can do a solid type bar of a robust size. You could also do rounds. You could do a variety of other things. You can do shapes. And the shape that is in the mold is what you get as long as you continue that shape all the way through the curvature and out the straightener. You can have a in-process shape to that material. very convenient, almost no processing at the end, other than make sure it's clean, cut it to lengths, and do what you need to do as far as processing. Finish processing. They need to be bored. They need to be various holes and or other things done to make it into the final piece or pieces. But this is a technique that can be used for very high speed, high productivity, and a wide variety of alloys. Now, it has to have a relatively narrow range of freezing on the alloy for this to work. Horizontal casting, and okay, it has bar casting, but and in this case it indicates a continuous cast aluminum bronze bar. That's one of the alloys that is better served by casting horizontally. There are others, aluminum bronze, nickel aluminum bronze, and some others. They have a long freezing range. The graphite die, or the die, it doesn't have to be all graphite, but that's better, is relatively long, or has a reasonable distance. The metal needs a dwell time in that die to solidify properly, and the extraction rate generally is slow, but this type of production technique lends itself to continuous casting of unusual materials. Again, the molten metal level is relatively high. You're casting out of the sweet spot, or the full area of the casting furnace, and you can cut it off in lengths. You can make different shapes. It can be not just a round bar. It can be a square. It can be a hex. It can be whatever you need it to be. It can be fluted. A lot of aluminum bronze and nickel aluminum bronze are used in a variety of applications where wear and toughness are necessary. They're also very good in seawater corrosion applications. In any event, and here's some examples of products that are made in continuous casting techniques. You have tubes. Now these are heavy-walled tubes. You have plates. There's a wear plate there in the illustration second from the left that is fairly thick. To produce that on a continuous basis, that can be, and if it's aluminum bronze or bronze, it can be continuously cast in a variety of ways, but usually that's a tough thing to do. But if produced continuously, it is beneficial. You can cut it off to lengths, take those over and drill them, put the whatever markings and or scores into it, finish the ends, things like that, and finish the product. On the far left, you see a wide variety of things that can be made. Sort of in the center, there's a star or multi rod that has multiple spindles to it that looks like a gear. And essentially, if you would cast that and cut it into short lengths or the proper length, that is a gear. You can produce lots and lots of gears very quickly that way. But you can see there's flat plates, there's unusual shapes, and obviously all this is cast because, and these shapes are because the die is that way. And all you need to do if you're casting the same metal in a cast horizontal form or vertical form is change the die and you get a different shape. Very versatile. Okay, another technique that is very unusual, and I'm used to this in several metal systems, but it's used in copper alloys. Centrifugal casting. Sometimes it's called rotocasting because you're rotating the work area. Metal casting process uses centrifugal force to form centrifugal parts, or essentially round parts, but of relatively thin wall thickness. And the wall thickness can vary depending upon how much metal is poured into this cylindrical casting, hollow casting piece of equipment, which is the mold, which is forms the shape. Now, how this is done, you have the mold preparation. That is a permanent mold. The permanent mold is reused multiple times. You pour the metal in there and you're rotating the mold at a relatively high rate of speed. So the molten liquid is thrown to the outside or the wall of the casting chamber, if you will. And then you cool, once you've poured all the metal there, you start cooling the casting chamber or mold, and you continue to rotate it during this process. When it is felt and the time is right, you open up the mold and remove the casting. And then whatever finishing processes that are needed to be done at that time are begun. Now, centrifugal casting is used to produce axisymmetric parts. You have cylinders or discs, which are typically, as I was saying, typically hollow. But that does not mean that the outside of this particular part, disc or a piece, needs to be perfectly round. It can have all kinds of different pieces or shapes to it. Here's a schematic of a general centrifugal casting technique. You have the mold. You have the mold, which is held in place by a series of rollers, and one set of these rollers are motorized. The motorized rollers impact the casting mold and start it spinning. You have molten metal at one end where the ladle is pouring into the holding chamber, pouring basin, and that at temperature is poured into this rotating mold. The RPMs of the mold are based upon past practice. Then it's cooled. As it's cooled, the part is formed or solidified into shape. And obviously, the casting mold is machined very carefully to produce whatever shape you would, or the final customer wants, save for some final minor machining. Then the mold is cooled. The mold being cooled properly and the solidification being done while the mold is still rotated so that there's no sagging or drips or anything. The mold is then opened and the finished casting is extracted. So you're looking at the bottom of this illustration and you have a finished casting. Now, like I said, it doesn't have to be a completely simple casting, such as this, or such as a tube or a pipe. It can be have lots of different shapes and bosses and attachment points. In this case, it's wider at the bottom or the left side of this and narrower at the top. It has 2 rings or cast-in rings of various types. This is very simple, but a very effective process. Produces a hollow part that can be used and can be custom designed depending upon the mold. Unusual process, isn't used everywhere, but can be used very effectively. And I'm going through this quite quickly, actually. Powder metallurgy. We've never addressed this in any of our discussions up to this point. Powder metallurgy is used in a relatively small percentage of the copper industry processing to make parts. Obviously, you start with powdered metals. Powdered metals of various sizes and shapes. The company making parts out of powder metals will order the powder from a powder metallurgy company that supplies it. The powder metal, in this case copper or other metals, may be produced in various forms, but a lot of times it's atomized into small particles. And once you have this, you can make a variety of alloys. You don't have to, you can get bronze or powder, you can get powder that is already brass. You can get powder that's already other metals or alloys. But in some instances, you can make powders out of 2 different, or powder metallurgy parts out of 2 different powders. One being zinc and the other being copper for brass. Or one being copper and the other being tin for bronze. It can be used to make unusual materials, such as a compact of copper and tungsten. And copper is a melting point that is in the between 1,000 and 2,000 generally, and then we look at tungsten, which is multiple thousands as far as a melting point. Tungsten is used to make filaments in light bulbs. Well, regular incandescent bulbs. They were highly incompatible, and I'm using this as an example, but you can put them together in a powder metallurgy compact and then sinter it, and you have a copper tungsten compact or part. Well, what do we do with powder metallurgy parts? Well, as the second item says, powder metallurgy is used to make unique materials impossible to form in other ways, or difficult to form in other ways, and maybe low volume. Well, powder metallurgy, you start, as I said, and here you have a metal powder, which is on the far left. And you have to determine what powder you want and what size configuration you want of the particles in that powder. You can get a wide variety of powders and wide variety of particle distributions. To make a good, strong compact, which is in the middle, you need to have determined what the powder distribution, and these are sifted. Powders are sifted or sieved to give you the right particle size distribution. You then compact it or press it together into a capsule or a slug, such as in the middle, and that is not the final size. It has a mild binder in there to hold it together many times. Then you've put it through a compacting piece of equipment that not only presses on it from a pressure standpoint, but also induces temperature or places temperature on it and causes sintering. Sintering basically makes sure that all the powder particles melt together. So you bring it up to a certain temperature in the sintering process, and pardon me, you end up with a solid material in the final form. I show a cylinder turning into a sphere here, but the final part size can be almost anything. Powder compaction press is shown here, or a typical. Obviously, there are newer ones, and ones that you may see at various companies are probably different. I just got this off the internet. The isostatic powder compacting is a mass-conserving shape process. The fine metal particles are pushed together in a flexible mold, and then under high fluid pressure is applied. The resulting article is then sintered in a furnace, which increases the strength of the part, and by bonding the metal particles together, melting them. The manufacturing process produces very little scrap. Obviously, you have a compact, and any powder that is not pushed together in making that compact is then recovered and can be reused. But you can make many, many different shapes, and one of the things that the jaws of this compaction press is basically a mold. So you're making a final product, you're molding it, you're pressing it, you're sintering it in a furnace, which is subsequent to this, and it shrinks during this whole process. But there is a very consistent technique in doing all this. You come out with a really reasonably good part on a consistent basis. So what can you make out of this? It's amazing what you can make. You can make gears, you can make flanges, you can make brackets, you can make various indexing teeth, you can make a variety of other parts, you can make tungsten carbide things, you can make cutting tools. You can make bearings and various washers, depending upon what you're using as a material alloy. and the compaction process and final shape. Essentially, you're making a final shape in the whole process. You're not cutting it to length afterward. You're not doing all that. You're making a final shape in this process. Much unlike many of the other casting or processing techniques where you make a long bar, where you make a long strip, sheet, where you make a long tube, rod or something like that, or fluted piece of material, you end up making the final size part. There may be some subsequent processing. It may need to be plated for or hard-faced for various applications, but essentially you have the final part size there. Well, here we are with another technique of casting, or metal getting into a final shape or size. Permanent mold casting. Well, many of us know that you can cast metal into a shape. A very old technique of casting metal into shape and used for lots of art projects or sculptures is called the lost wax process. You basically produce a mold. It ends up being filled or out of wax. You make a cast plaster of Paris or something else around that. And so you end up in that particular type of semi-permanent mold, making a mold, but the wax is still in there. Then you pour molten metal into it, the wax evaporates or leaves, and you have your part. Now those are one single use. In a permanent mold casting, the mold is used over and over again. And the molds are usually made of metal, and there are several different types. The types of permanent mold casting include gravity casting, in other words, you pour it in by gravity. Slush casting, the metal that's being poured in is semi-solid. Pressure casting, you push it into the mold. Vacuum, you basically pull it into the mold. Typical products that are components such as gears, splines, wheels, gear housings, pipe fittings, fuel injection housings, and automotive pistons, internal combustion engine pistons, are done in these processes. And some of these are very high productivity, relatively speaking. A permanent mold casting using what's called a book mold. Here's a book mold. It's a two-part mold. You're making tin soldiers. You have one side and the other side, and you put them together, it looks like a book. You have some holes at the top where you pour the metal in. The third illustration or picture, as you go down, the casting is done, it's cooled, you open the two sides of the mold up, and you extract the parts, and then you finish them. There's always a sprue at the top, and maybe some runners and some extra metal. You have to clean all that off. Usually all those pieces of metal are thrown back in the pot for remelt. You clean and finish, and there you have it. Generally the parts are that way. This is just a little bit above a lost wax. Permanent mold casting in larger molds. These can be hand worked with or on a machine basis. They can have a core, as illustrated in these, or no core. So they can have a hole in the middle of something. It can be a round part with a hole in the middle, or it can be a solid piece. The casting mold can be big enough to produce multiple castings or multiple pieces in one, or the casting may be large enough that you're only producing one in a mold. So you start and you pull put the core in, you push the two sides of the mold together, you pour the metal in, you let it solidify, and you cool the mold. You open it up, extract the part, and you may have to put a new core in and lubricate the mold. Permanent mold casting products. A wide variety of things, believe it or not. Some of this is sometimes called die casting. So here's copper, alloy, permanent mold casting products or items that are produced. Obviously, the big round plate with the that's maybe produced one at a time, whereas the other illustrations shown in this photo may be produced multiples at a time in a casting mold. So depends on what you want to make and how big the product is, but you don't have a whole lot of finishing to do. There may be some minor cleanup and maybe a little bit of drilling and or other final processing, but it's pretty much a final product. So that I've covered a wide variety of techniques of producing metal, copper alloys, into a wide variety of products. Now, some of them are high volume and some of them are not high volume. Some of them can be made high volume. I'm done with that. I think we have about 8 minutes left, according to my watch. I don't know whether anybody has any questions.
Yes.
I appreciate all of you being on this webinar. I hope it's been important or interesting. And let me know if you have any comments or concerns, questions.
All right, thank you, Jim. Once again, please submit your questions using the tab on your webinar toolbar. We'll give it a minute or so for people to type in their questions.
And I would say I appreciate all the people that have joined the webinar as we've proceeded. It was very gratifying to see them all come on. So that was helpful. I would point out that Copper and Brass Service Center Association has asked me to present this webinar as a lead-in to their plant tour, which is upcoming on bunting bearings, which is, I think that's in Holland, Ohio. Is that correct?
Correct.
In early September. And if you attend, hopefully you can attend, many of these casting processes and powder metallurgy technique are utilized in their facility or facilities. And that's why we've been talking about this. They produce a wide variety of products in a number of alloys. and and it's a very interesting, should be a very interesting tour.
Yeah. Okay, Jim, we haven't had any questions, but as a reminder, if you think of questions throughout the day, you are more than welcome to email me and we will get them passed along to Jim and answered. Once again, I would like to thank Jim and everyone else on the line this afternoon. Make sure to mark your calendars for Friday, October 6th for our next e-training webinar, A Good Year Ahead. This will be our yearly economic forecasting webinar presented by ITR Economics. And for those of you on the Service Center side, we look forward to seeing you Wednesday, September 20th at Bunting Bearings. Thank you.